All right, here we go. Hello, everyone. My name is Sai Venom, and I'm a developer advocate with the Amazon EKS team. But today, we've got three experts from AWS for an exciting topic. We're going to be talking about how to fine-tune AI models, much like the foundational models that power chatbots like ChatGPT. Fine-tuning these models to give you precise responses to areas of kind of specialized focus. I want to go ahead. First, folks that are watching at home, drop a comment. Let us know where you're tuning in from. Also, let us know how you think AI might revolutionize your industry, maybe your hobbies, things that you do over the next decade or so. And as we get into today, hopefully we'll find some overlap with some of the things that you bring up. First, I do want to introduce my awesome guests here. Ravi, I want to start with you. Tell us a little bit about yourself, what you do at AWS. And look, I've got to ask you, AI and ML technology has been around for decades almost. Why do you think it's really just getting popular now?
Yeah, thanks. So my name's Ravi. I lead our compute go-to-market, continuous go-to-market for our ISV and digital native customers. So I've been in the container space for about 6 years or 7 years at this point. I used to work on Apache Mesosphere at the time. Uh, uh, we've been like working with customers at one point. I know as Kubernetes has grown over the years, there've been support for many new things, including different data workloads and different type of AI ML workloads as well, right? So it's not really a new thing. Like folks in the Kubernetes space have been building various kinds of ML technologies, ML platforms, ML frameworks for the longest time. And that's how I got involved. I got engaged with the community. Now at AWS, we work with a lot of customers who are deploying EKS, for example, and bringing new kinds of building new kind of product experiences for their end users and using different ML frameworks to be able to do that on Kubernetes.
Awesome. Thank you, Ravi. And excellent response there. I think there's definitely kind of a golden age for AI that we're seeing here. I think sometimes when you look at how the internet was in the 90s, you can really compare that to, how AI and ML use cases have been burgeoning over the last few months and even the last decade. Lucas, I want to go to you next. Tell us a little bit about yourself. And I have a question for you as well. So we talk a lot about AI and ML, but today our focus is on generative AI. How is generative AI different from traditional AI and ML use cases?
That's a great question. So let me start by saying hi and thanks for having us here today. It's our pleasure to be here and very exciting to talk about generative AI on top of EKS. And I'm Lucas. I'm a content specialist. I work a lot with Ravi, so we are partners in crime here, supporting our ISV customers. And I've been working with Kubernetes, I think, for the past 5 years or so. So I've been in a long journey ever since like Kubernetes 112, 111. Ever since I started my career working as a SRE, as a DevOps engineer. I've been in AWS for the past 3.5 years, will be 4 years next year, and I've moved all the way from Brazil to Austin, Texas. So this year, size from Austin as well. So I've been in US for about 1 year right now. It was like 1 year, I think, 1 week ago. And going to your question, Sai, how generative AI differences from AI ML, I think is the way that the data. I think like to start is the way that we structure the data, right? So before we use it to have supervised learning, unsupervised learning, reinforcement learning, and now those kind of learnings would require a structured data set, or we would need to identify those features and labels. What is a good thing and a cool thing about generative AI is that you can have unstructured data, and the model itself has so many parameters. And in the case of the demonstration today, we're going to be using a 7 billion parameters model. So you get all those parameters and train a model with all those parameters probably for weeks or even for months. And then you can have that model to do very specific things based on your needs. So before we would use machine learning to define if the picture is a cat or a dog. Now you can actually produce things. And I like to say that the AI, it's almost like the new internet, and it's gonna revolutionize the way that we develop code as well, helping the developers, not replacing them.
Excellent. And welcome to the show, Lucas. And I got to agree with Robert here. That is a heck of a move. And welcome to the States. Welcome to Austin. That's, like you said, that's where I am as well. Look, I actually saw something really interesting the other day. I like that you talked about how AI helps you produce images. I was looking into how it all works, and I saw that it reminded me of a joke from back in the day when they would take a blurry image and say, enhance, enhance, enhance. And really, generative AI is a lot like that, where you start with noise and you continue to enhance that image from pre-trained models, and then you end up with a beautiful image. But today we're not going to be talking about generative AI for images, although I believe the techniques we're showing can be applied for images or large language models. So excellent. I want to move to my last guest here, Gabriel. Look, Gabriel, I've got a question for you as well. Now, when we actually, Andy Jassy very recently talked about AIML, of course, CEO of Amazon, saying that building really good AI models takes billions and billions of dollars. But he goes on to say that, while most companies and individuals don't have those types of resources, being able to take an already built foundational model and fine-tuning it, that's really where a lot of folks are going to get value. Gabriel, I hope you're going to show me today that we don't need billions of dollars to build an AI model. So tell us a little bit about what you do at AWS, where you're from, and also tell us what you think about, what we're going to be talking about, and show us a little sneak peek of the demo today.
Nice. So hello, everyone. My name is Gabriel Martini. I have been working for AWS for 6 years as solutions architect. I'm based in Brazil. So I have been working with different use cases here in Brazil for machine learning. So I have been working with education, for example, helping students to improve the learning. I have been working with teachers to correct exams, for example, utilizing generative AI. And also, I have been working with public sector. So, for example, we have a judiciary system here, for example, working with machine learning to summarize, process, identify, and classify text. So there are a lot of use cases that we can utilize. And answering your question, Sai, for now, with different models, with pre-trained models, with foundation models that are available for everyone because of researches and different providers, we can separate in different kinds, in different types of customers. So, for example, we can have consumers that just want to utilize this model, these foundation models, to bring value to the business. So for it, for example, we can exemplify with the AWS Bedrock. So we don't need to spin up a cluster or train a model. You can utilize this with a serverless approach. And of course, you can train your model from scratch, but with new technologies, as we are going to show today, you can utilize these on demand. So you don't need to buy GPUs and for a long time, since you can utilize the AWS cloud to spin up a cluster and train and fine-tune your model.
Awesome. And so I'm guessing we don't need billions of dollars to make really good AI models. I think Andy Jassy was talking about our recent announcement of Amazon Bedrock. But look, we're going to be seeing a lot of that today. Gabriel, could you show us a little sneak peek of the demo you've got planned for us today?
Yes, of course. So the problem that we're going to solve here, it's a common problem for many customers. So for example, we have these foundation models. These foundation models are really good to generate text and sometimes answer questions, but it's not a domain-specific model. So in this example that we're going to show, for example, we want to create a question answering chatbot that is able to answer financial questions, for example. So for financial questions, we have a specific vocabulary, a specific way to answer. And how can we do this? So I'm going to show a no fine-tuned model, so a default model. For example, let's say if I have this question here. So why do I need an emergency fund if I already have investments? and this foundation model, without fine tuning for domain specific task, it's going to generate a general answer. So let's see the answer of the model. Sorry, Sai.
No, you're good. And Gabriel, I just wanted to ask, what foundational model is this using?
Yes, here I'm using Falcon 7 billion of parameters. So it's not the hugest model, but it's a good model for question answering. So here, for example, it answered in a general way. So it's not a really good answer. It's not as expected for a financial advisor, for example. It answered, it's pretty simple. So you need an emergency fund because you don't know when you need it. So it's not a good answer, right?
Pretty basic
So
answer.
yeah, we are going to show how we can improve this utilizing EKS and other technologies that we're going to use.
Right, it's pretty vague. And look, the other thing that I think, we just got a comment in the chat as well that, the future of domain-specific models at scale is going to be a game changer. Because so many companies need the ability to fine-tune models. There's concerns around data privacy, putting all of your personal, maybe financial data out on the internet, and to be able to provide you answers that take the right set of data, when providing those answers. So I know there's a lot of different ways to do fine-tuning of AI models. There's a lot of different approaches to how all of these things could work. But today we're going to get really tactical and show one approach to fine-tuning models, right? So look, without getting in your way anymore, I want to let you take the stage here. Show us a little bit, about what you're going to show today and how you can fine-tune that model to make it a little bit more accurate.
Absolutely. I think we can. I think with that I can start. Thanks, Sai, for the comments and the introduction. So the model that Gabriel showed us, actually, I see my screen right now. I think so, right?
Yep.
Okay, so the model that Gabriel showed us, it's a non-fine-tuned model, so it just replied in a very basic way, right? Not like a financial advisory should reply to us. Now we're going to showcase to you folks a structure or a platform, I would say a solution that can help you to fine-tune your foundation models with all the components running within Amazon EKS. So let's dive deep first on the problem. Why won't you give us an introduction around the problem, Gabriel, in a business standpoint? So why would we want to fine-tune our models? I think we said a little bit, but if you can give us an explanation around that.
Yeah, so for example, in this case, we want to have a better answer. So we have a specific domain question, and we have a specific vocabulary that we are expecting to the answer. So this is one use case. But for other use cases, for example, you don't want to create a chat application. You want to create a classification application, entity recognition application. So the foundation model is good to generate text, but it was not trained for a specific domain task. So this is a little bit why you would need to fine-tune a model.
And this is for the business standpoint, right? But let's take a dive deeper around on the infrastructure and research standpoint. Running those AI and machine learning models, it's not really a walk in the park. It's not so simple. It's not like you deploy in Kubernetes and you are done. Many people think it's simple like that, but you actually need a robust and scalable infrastructure that will adjust based on your needs. This is where EKS with the add-ons and controllers comes in place. Thanks to Kubernetes and thanks to Kubernetes powered with Amazon EKS, AWS resources, and projects like Karpenter, we are able to get a fantastic option for scaling our training and serving workloads. So let's dive deep on the high-level overview around the architecture, what we have. So first of all, I know that we already have an episode around Dayton EKS, but this entire stack, it's powered by Dayton EKS. If you don't know the project yet, please, you definitely should check it out. So let's talk about the add-ons that we are using, right? So we have JupyterHub. JupyterHub, it's basically a hub of Jupyter notebooks. So you can actually go there and get one notebook for yourself. And you can have multiple profiles and each profile tailored to a specific container, image, or Karpenter provisioner. Since we are talking about Karpenter, Karpenter is the second add-on, as you can see in the high-level overview. Karpenter is used for scaling the nodes. And just to do a quick comparison between Karpenter and cluster autoscaler here, different than cluster autoscaler where you need to define the instance type beforehand, Karpenter, you can define the instance at the time that you want to spin up, that you have a pending pod. So Karpenter is able to provision the nodes based on resources, not based on instance types. Then we have Airflow that we are not going to be using in today's presentation, but we are going to include in the solution that we are presenting for you folks right now. And last but not least, in the add-ons, we have GPU operator that will be responsible to configure the GPU nodes for us. So when you are spinning up GPU nodes, you will need drivers and additional libraries installing on those nodes. So in order to have it and don't needing to manage base images, base AMIs, you can use the GPU operator. So whenever you spin up a node with GPU operator will notice that and we run a daemon set in that node, and in that way we'll install the libraries. So with that, those are all the add-ons, but now let's talk about the core component of our stack today, who is Ray. Why, Ravi, won't you give us a brief explanation around what Ray is and how our customers are using Ray?
Yeah, sure. So Ray basically is a framework for scaling and optimizing your AI ML application, right? So as you see here, it consists of the core distributed runtime that it has and a set of libraries for simplifying the ML compute in this case. Now, one of the things we talk to a lot of customers, and as part of those conversations, we've seen customers leverage machine learning to power different kind of experiences or many aspects of product experiences that they create for their end users, right? And they leverage these techniques to be able to build and scale different kind of ML workloads. Now, along with that, we've talked to some of the customers who now adopted Ray specifically to be able to build their ML platforms for things like model training and even inference, and who found that the data science approach that Ray provides, so the data science friendly approach that Ray provides, or Ray Surf provides specifically, offers, for instance, it's a great match for what they're looking for, right? So the abstraction of how different personas within the company, the data science within the company, can use the Ray Surf ecosystem and that friendly approach to the data science to be able to do that is a great reason why we see a lot of customers adopting Ray. Now, with that in mind, what Lucas, Gabriel, and the rest of the team here have done here is build out this reference architecture that you're looking at, or the demo that we'll be going through for fine-tuning large language models on EKS and building this ML platform, right? So Lucas talked about the data on EKS project, the set of blueprints that is powering this platform, but this would be an end-to-end demonstration of how we're trying to bring everything together.
So I've got to ask one question here, Ravi, that, we're looking at Ray in the context of Kubernetes, but, why Kubernetes? Why do we need to use this distributed container orchestration management solution for AI ML training and specifically Ray?
Yeah, for a lot of cases, we have seen that customers who are already on Kubernetes or using Kubernetes for running different kind of workloads already. It's standardizing on Kubernetes for bringing any new additional type of, let's say, data workloads or even ML workloads, in this case, running Ray on EKS or Ray on Kubernetes is a great reason, right? So the standardization piece is a big thing that we see a lot of customers choosing Kubernetes as the underlying layer and making sure the deployments of different kind of tooling and workloads for their teams is consistent.
Got it. And, sorry, just to quickly interject here, we got a comment here from Robert. Try to explain Kubernetes to a friend rather. Then we both didn't understand it. Look, common. This is common. Now, I think the solution to this and what you guys are going to cover today is how there's two different caps here. One of them is going to be the data engineer. This is the guy that actually needs to know. Guy or gal that needs to know how Kubernetes works. How does the underlying technology work? Meanwhile, we've got the data scientist, and that person is really abstracted away from the underlying complexities. And I think that's a really interesting concept here, that we're making experiences where you don't really even need to know that it's Kubernetes underneath the covers to be able to run these really powerful training models. So I'm sure we will get to that as we get through the demo here, but I'll let you keep going here, Lucas.
Absolutely.
On that piece specifically, let me add to that, right? If you're a data scientist, you don't really care about Kubernetes, right? Just to add to your what you were just talking about, or even a machine learning practitioner, right? All you care about is you want to leverage a framework tooling like as part of your ML stack, which lets you scale your ML jobs without needing to understand much about the infrastructure, right? So Ray, in this case, and we'll talk about it a little bit in detail as well, helps you distribute those ML workloads across different types of compute node setups and GPUs, but providing that experience for our data scientists that they care about. If you are, let's say, an ML platform builder or an ML engineer, right? So Ray provides those kind of abstractions for creating these scalable ML platform. Also providing a API, the ML API that simplifies the onboarding and the integration with the broader ML ecosystem, right? On the flip side, if you're a systems engineer, right, or a distributed systems engineer, platform engineer, Ray provides or handles the process around like orchestration, scheduling, fault tolerance, auto scaling, right? So it provides those experiences for different personas which exist around someone who's trying to build an ML platform.
That's correct. Yeah, that's correct. So why won't we get started? Because I think like we are excited here. We are gonna show all that to folks here in today's presentation. So let's talk about the flow of the demonstration that we have. So very well explained by Ravi and Sai. We have two different personas. One is the data scientist and one is the data engineer. The data scientist doesn't need to be aware of Kubernetes. You just need to know how to experiment and access those resources. So this is exactly the role that Gabriel is gonna play. So Gabriel here, our data scientist for today's video, it's gonna do an experimentation in JupyterHub. So he's gonna craft both the training and the serving script, and then let the cluster, the training cluster, and submit that training to the training cluster. One thing that is important to mention for this demonstration is that we already have pre-deployed a training cluster. So we already have a Ray training cluster up and running for training a workload. This can enable us to submit multiple trainings at the same time, but we are gonna provision the serving clusters on demand. So basically, based on our needs, we are gonna use the Ray operator mechanism to provision those those serving clusters, and also deploy the applications in there. So going back to your previous question, Sai, why Kubernetes? This could be a good answer as well. So Kubernetes, since it has the controller and the operator model, it extends the API server capabilities by including cluster resource definitions. And because of those cluster resource definitions, you can standardize your stack in YAML files in a declarative way. So many people who are already using Kubernetes prefer to do that because of controllers and operators. So I think we are ready to see some action, right? So why won't we get started with Gabriel? So since Gabriel is going to be the first persona here, he's going to create and craft and explain all about fine-tuning for us.
Awesome.
Nice.
Off to you, Gabriel.
Okay, so after Lucas, as the person of the machine learning engineer, he created the platform for us. So here I'm at the JupyterHub. As data scientist, I'm going to utilize the JupyterHub as my development environment. So here I'm creating Jupyter notebooks and create scripts to train, test, and do data experimentation. At this time here, in JupyterHub, this environment here, I'm utilizing CPU. But why CPU? Since here we are working with large language models and we are going to need GPU for this. So at this time here, I'm not doing any kind of training or serving these models. I'm
From
just
the notebook.
Yes, from the notebook. I'm just in developing my scripts. So I don't need GPU for now, because after I'm going to use Ray to start my training and test my scripts. So for this case here, JupyterHub, it's a good solution because we can set up different profiles in JupyterHub. So we can have a use case that I need CPU, and we can have another use case that you need GPU in my development environment. Lucas, could you say a little about JupyterHub profiles and how EKS can help on this?
Absolutely. So going back to my screen right now, when you deploy the stack that we have available through Dayton EKS, you're going to get presented with those multiple different profiles. So those different profiles can be assigned to specific personas in your organization. So in this case, Gabriel is getting the data engineer CPU because he's not doing any GPU tasks in the notebook instances. All the tasks related to training and serving will be done on Ray. We are just using notebooks to craft the scripts. So this gives us the ability to pick the best profile. But how we guarantee that this profile will be associated with the right instance type? So as you can see here, we have data engineer that will provision CPU instances. We have training, we have inferentia, we have data scientists with GPU plus time slicing. And time slicing and me here is just way to micro-partitioning GPUs. We have a bunch of blogs, and I'm not going to touch upon micro-partitioning right now because I would be speaking for more than 30 minutes only about micro-partitioning here. But we have all those blogs. But now let's see the actual configuration of the Jupyter Notebook. So this is one of the configurations that we have available through Dayton EKS. There's going to be a blog launched about that as well. But I want you guys to pay attention on this. So as you can see here, this is the manifest to install JupyterHub, and we are installing that using Terraform, Dayton EKS add-ons. And as you can see here, we have the profile list as a list. Under profile list, we have data engineer, and we have all the multiple profiles. One thing that I want you folks to pay attention is the Karpenter provisioner. So we are using some placement constraints on Kubernetes to associate the right profile to the right Karpenter provisioner. So in this use case, I'm associating the data engineer CPU with a default profile. I'm associating the data science GPU plus time slicing with another profile who is the GPU time slicing. So this gives us the ability to pick the right instance type for the right time for the right persona for us. And Karpenter is a very powerful solution to do that, because how would we set up different nodes before Karpenter? It would require cluster autoscaler, it would require provision those autoscaling groups, it would require configure the deployment of cluster autoscaler and the expander, like a lot of configuration. Karpenter just simplifies that for us by leveraging provisioners, who is another custom resource definition using the controller/operator model. So you can use those custom resource definitions to configure your nodes. So in this case, we have specific provisioners for specific personas, because thinking next steps, maybe you don't need the same node for training and serving. Maybe you can train in some bigger nodes with more compute capacity and serve those in smaller nodes and smaller instance types. This is exactly what we're going to show in the demonstration today.
So Lucas, I just want to point out one thing. This reminds me a lot about, building internal development platforms, IDPs. It's very similar where, yes, the data engineer has all the power of choosing the nodes and the different profiles and configuring the provisioners, which align with the right type of nodes. But the actual data scientists, they need guardrails in place. You want to make sure that they're using the right type of nodes for the right type of workloads, and you can make that decision for them and serve it in a beautiful dashboard where they don't have to go click around in the dashboard, pick the right type of nodes, do all that kind of research on their own. They can be confident that that engineering team has done that. And I just want to point out, there's a comment in chat showing that, Suyash did exactly that with EKS. Basically, the engineers and scientists don't need to really know the Kubernetes underlying pieces. You just leverage EKS in this kind of IDP type platform. Very quickly, a couple of questions that came in chat. Lucas, I know you showed those kind of configurations in Git. Does JupyterHub integrate with version control so that, scientists can work directly in Git for stuff like this?
Yes, you can integrate GitHub, you can integrate any SCM. It's like, at the end of the day, it's a Docker image, so you can do any kind of automation that you want to do to leverage those requirements to your developers. But yes, it integrates well with GitHub. You can clone your repositories, you can do anything that you want to do.
Excellent. And one more quick question. Will Karpenter automatically scale down? Will it destroy nodes once the workloads are done running? Or are you going to rack up a big monthly bill from nodes sitting around?
I will cover that during the demonstration because I think it would be better. So Gabriel, back to you, to the notebook script.
Let's do it. And Gabriel, just a pointer, if you can make that a little bigger so we could see it.
Okay. So now I'm here at my notebook, my Jupyter notebook. And as the first thing, as data scientist, what I'm going to do here, I'm going to import all my dependencies in this image here. So there are some cool dependencies, cool libraries that Hugging Face are working on that we can utilize for generative AI. So for example, we have the Transformers library that we're going to utilize here. The Transformers library, we can utilize different pre-trained model, foundation models from the Hugging Face community. So we can load these open source models and try to test them. Also, I'm going to utilize the PEFT library. So PEFT is a new library from Hugging Face also. And this library here will help us on the fine tuning process. So it implements different approaches for fine tuning, and we are going to cover one of them today.
Excellent.
So, okay.
And Gabriel, if you could make that a little bigger so we could see it, that would be awesome.
Oh,
and
sorry.
for the folks that are following along and want to be able to use this notebook at home, I dropped a link here as well.
Okay, is it good right now?
Looks great.
Okay. So as I said, the Transformers library, we can choose different foundation models. In this case here, we are going to show the Falcon 7 billion parameters model, but you could change for other models like Llama 2 from Meta, GPT-J, Falcon Lite, Lite GPT, and so many other models that you can utilize with the same script. Okay, so as we explained it, we have the ray clusters. And with the ray training cluster, we can do different experimentations, test different models with ray. And one cool thing that we have for the data science team, we can utilize ray APIs from Python. So ray has a Python library, and the data science team that already knows Python can utilize these libraries to interact with the cluster. So at this stage here, I'm importing the ray library, and here I'm connecting to my ray cluster in EKS.
I think we lost it. There we go. We're back.
Back.
Yes.
Okay. So at here, I'm connecting to this cluster, and I'm also installing all my train dependencies in this cluster. So I don't need to have pre-built images. Also, I can create this. But if I have new dependencies and new libraries, I can install this during my session. So at this time here, after I create my connection, we can visualize my connection in the ray dashboard. So here, for example, I'm at the ray dashboard. I can go to the jobs here, and I can see that I have a session running. So basically, I connected my Jupyter notebook with the ray. So for now, I can run my scripts in ray, deploy or training scripts in the ray cluster. Okay, so the first step that I'm doing here, I'm going to experiment with the default model. So I'm going to serve the Falcon 7 billion parameters model without any kind of fine tuning. So as I showed for you at the beginning, we have this application here with the Falcon 7B model deployed. And it's pretty easy to deploy models with Ray API. So basically, I can create a deployment class as I would create a deployment script. It doesn't have so much specific things that we need to change to deploy this on Ray. One thing that we can do is to utilize the Ray decorator to specify the number of GPUs that you are going to need for this deployment. So in this case here, we are going to utilize just one GPU for this model. And here, it's a simple script utilizing the Hugging Face libraries. So basically, I'm loading the pre-trained model, the foundation model. And here I'm receiving the requests, the prompts, and answering back with the model answer. And to start this application in Ray, basically, I just have 2 lines of code. I need to start my serve in Ray, and after I can run my deployment class in Ray. So Ray, it's going to deploy this application there. Let's show the results of this. So if I go here in Ray, I can go in serve, and you can see that I have a health status here, and I have an application here that is deploying. Right? So after it finishes to deploy, I can start to do my requests for this endpoint here.
So, Gabriel, this is going to be the trained model here that we're working against?
No, for now, I'm just showing as the first step the full model, the no fine-tuned model. Okay?
Got it. And that's why it's just serving. There's just one deployment running. There's no crazy model training, scaling up of GPUs. We're just looking at the existing model and how to serve it. Got it.
And probably using Jupyter notebooks is not like do everything through notebooks is not the best way to scale. It's only the best place to do experimentation, the way that Gabriel is doing. So now that he's satisfied with his model, he knows that it deployed. We can go and talk about fine-tuning with contextual data.
Got it. So this is the background of the demo you showed us at the very beginning. Just how did it work in the first place? Got it.
Exactly. Yeah. So my application is up and running, and if I ask any questions, it's going to answer for me like I demonstrated at the beginning. So it's good for to explore these foundation models and see if it's needed to fine-tune that model. So at the beginning, if I receive a business case, I'm not going to start to fine-tune the model at the beginning. I'm going to see if the foundation models that are already available in Hugging Face, for example, can do a good job for my specific task.
Fulfill your requirements. And this is where maybe we need to start to analyze if we would actually need to fine-tune a model or implement RAG or something like that, right, Gabriel?
Yes. So for some cases, we can utilize a RAG. RAG is a technique to bring context to the models. We can comment about this after, but we can test different techniques without fine-tuning to see if the foundation model can achieve these requirements that we have.
And Gabriel, what is ragging for anyone who might not be aware?
RAG is it's the name for retrieval augmented generation. So basically, you can, for example, preprocess documents, web pages, mainly internal web pages that are not public, and you can preprocess these documents, store the text from these documents, and utilize this text as context for your foundation model. So, for example, if you have internal wiki or internal documentation with it step by step to solve a problem, for example, this kind of data was not utilized to train a foundation model. But you can get this private data, store this private data in what we call a vector database, for example, OpenSearch or ChromaDB or Pinecone, and you can store this in vector database. And every time you do a question to the model it's going to get the context from this vector database and bring this context to answer your question. So it's a way to avoid hallucination in models.
How is it different from the fine-tuning approach you're going to show today? RAG versus, LoRa, I assume here.
Nice. So I'm going to show in a few moments. So I'm going to hold to answer quickly.
Okay.
Okay. So as soon I tested the foundation model, I can delete my application. So I don't need to hold this computational resource. After Luca's going to show the provision and the shutdown of this instance. But let's say about the fine tuning. So in some case, you just don't need, you just not need the context to answer the questions. But for example, you need that the question utilizes a specific vocabulary or has a specific template. For example, in a case that I have been working here in Brazil, you have some judiciary documents, and these documents have a specific template. So it has this kind of title, it has this kind of abstract. So you have a template for that document. With just utilizing RAG, you are just bringing context. So basically, the foundation model can answer your question correctly, but it's not going to answer in that format. Should the model answer in that format, we need to fine-tune this model. And what is fine-tuning? Basically, fine-tuning, it's a way to customize this language model. So basically, it's going to get the neural network of that trained model. The model was trained before. This is why we call pre-trained model. And we get this trained model, this neural network, and try to adapt this neural network. So for example, when we do a full fine-tuning, we are basically retraining that model. You are changing, for example, the weights of the neural network to try to force the model to output as we expect. But this kind of thing here, fine-tuning, can take a lot of computational resources. So when we do a full fine-tuning, we are talking about weeks or months to retrain this model, and we have the risk to the pre-trained model forget the pre-trained data, and the model is not able anymore to answer your questions. So it's a risk. And we have different approaches to fine-tune a model. LoRa, for example, as you commented, LoRa, it's the name of low ranking adaptation. So we don't do a full fine-tuning when we are doing LoRa. Basically, with LoRa, we maintain the trained model, we maintain the neural network of the pre-trained model, and create what we call of adapters. And these adapters are new layers in this neural network that are adapted for our training data. So with LoRa, we have lower time to fine-tune a model because you are not doing a full retraining. And also, we are specifying our model to that specific data.
So I'm curious. So it almost seems like we're building a layer on the foundational model.
Yeah.
Does it potentially impact the speed at which, when the model is trained and served, how quickly it's able to process user inputs and produce answers?
Yes, it really impacts in the time of the training and in the time of the serving. But also, it has some trade-offs, right? So for example, if you are adapting for a specific use case with LoRa, you can do what we call of overfitting the model for that specific use case. So you need to, based on your use case, you need to choose the best approach. You have some trade-offs for every approach here.
Got it.
This approaches here are pretty new. For example, LoRa was introduced in 2021, so it's a pretty new thing. And we have also QLoRa. QLoRa was introduced this year, 2023. And QLoRa, it's another approach that it's good for small clusters. With QLoRa, for example, we can utilize less GPUs because we do floating calculations with less numbers. So, for example, for LoRa and full fine tuning, we are utilizing 16-bit transformers. So we're doing calculations with 16-bit. And for QLoRa, for example, we can utilize just 4 bits. And with this, it's possible to utilize less GPU memory. And we can also utilize CPU memory to offload the GPU memory. So with QLoRa, you can have a small cluster to train your model. But of course, it also has trade-offs. So for example, for QLoRa, we can see some the quality of lower quality of accuracy in some use case. Okay, so at this demonstration here, we are going to utilize the LoRa approach. So after I selected the approach that I'm going to fine-tune the model, the first thing that I'm going to do is to check my data set. So this data set here that I'm going to utilize, basically I have instructions, so I have questions, and all of them are financial questions, and I have outputs with the right answer for that question.
Okay, so just to remind folks, when we first saw the non-fine-tuned model, we asked it a question about why do you need to keep investments? Why do you need extra emergency funds if you have investments? And it came back with a pretty simple response. Oh, well, what if you don't? Or what if you run into an emergency? You need the additional, emergency funds. Not a great response. So, what I'm seeing here, Gabriel, is that this data set probably tons of questions and answers related to financial questions. But what we'll see is that using this, ideally, it's going to be able to get us a better response in the end, right?
Exactly.
We hope if the demonstration works.
Let's see it.
Yes. And one cool thing that we can achieve with LoRa, you don't need a huge data set for fine tuning. So for this demonstration here, you are going to utilize just 1K examples here. So we have just 1K questions and answers. All right, so let's start our fine tuning. So after I have my data set, I'm going to create my training script. And this training script, basically, I have my foundation model that I'm going to utilize as base of this training. So I'm going to utilize the Falcon 7B. I have here my data set name. And after I prepare my data set, so basically in the preparation of data set, I'm here changing the name of columns just for demonstration. But after this, I'm loading this foundation model utilizing the Hugging Face library, as same as did in the deployment script. So I'm loading the model here. And I'm configuring the LoRa hyperparameters. So hyperparameters, the work of data scientists is try different hyperparameters and see which combination is the better for that task. And one great thing that we have with Ray, we can set up the scaling config for this training. So the data science knows what is needed to train this model, to fine-tune this model. So in this case here, I'm passing the number of works needed, So here, if I'm not wrong, we are going to utilize 8 instances to train this model. And we can pass the resources we need if it's going to be GPU or CPU training. In this case, you are going to utilize GPU. And another great thing that we can do with Ray is pass a storage path. And this storage path here, it is what we call of checkpoints. So this kind of fine tuning can take hours, days, weeks to finish. And with storage path, Ray can store checkpoints. So for example, in each iteration on the data set, it's going to save that model, that temporary model, in Amazon S3. So it has integration with Amazon S3. And if my cluster dies or if something fails during the training, that checkpoint is stored in Amazon S3, and I can return my training from that checkpoint.
So Gabriel, I gotta ask. So I'd imagine the most ideal use case here is if you're using something like Spot instances, which are going to come at a great discount. But look, Spot capacity might run out, and AWS will give you 2 minutes to shut down the workloads. Let's say it's been running for 2 days. You're not going to lose all 2 days of training, right? That's what this comes.
Yes, that's right. So it's a great use case to utilize the Spot instance. And with Karpenter, it's pretty easy to set up this kind of environment. Okay, so I created my training script. And what I'm going to do now is to save this my training script in Amazon S3. I'm doing this thinking about, for example, to create automations, for example, to retrain my model every time I change my script or every time I change my data set, so I can start my training based in the S3 events, for example. So I'm storing this script in S3. And after this, I'm going to call the Ray job submission client. So basically what is happening here, I'm connecting to the Ray cluster, and I'm creating a job in Ray cluster. Same for the Ray cluster to download my script from S3 and start my script. So basically, it's going to run the script I created in the notebook.
So Gabriel, just so I understand, so everything is still running let's say I've got an EKS cluster here. JupyterHub is right here. All of the commands here so far have been running in Jupyter, but I've also got Ray here, like the Ray operator, that's able to drive and create nodes or clusters or whatever to be able to run the actual training job that we've built here. So Ray is just sending it over to, JupyterHub is just sending it over to Ray, all in the same cluster. Is that right?
Yes, it's that right. So what we are doing here, we are saying to the Ray to provision this capacity for the training job, and we are going to see and monitor this job in the Ray dashboard. This is what Lucas is going to show for us.
Exactly. So going back now to the Ray dashboard, as we can see here, we have 2 connections. One connection is the connection between the JupyterHub and the Ray cluster.
Lucas, just a little bit bigger, please, before you get into it. Sorry to interrupt.
So this connection is the connection between Gabriel and JupyterHub and Ray cluster. If Gabriel closes the connection right now for me on JupyterHub, we should be able to see that connection closing right now. And this is the job that Gabriel just submitted. As you can see here, we are able to see that the job was actually executing everything that we defined on the training script, and now it's actually running. If we go to the Ray cluster, we should be able to see the GPU memory increases. There we go. So right now, it's actually training our model. As you guys can see here, we are using a lot of compute power. So we are using almost all the entire memory for my G5 4x large instance, right? So, but let's say that right now, after my training is done, I don't need that cluster anymore, right? I don't need those instance types. And going back to the question that was asked before that I said I would answer right now. So this is the power of Ray running on Kubernetes. Let me increase my screen real quick here. So this is the way that we have configured the Ray cluster, right? So this is on the repository that you can have access after the video today. So please just remain here to watch, and then you can go to see the repository. So for Ray, we have to configure two things. We have to configure one head node, and we have to configure one worker node. For the head node, this is where Ray is gonna to orchestrate all the worker nodes for us. So the job is sent to the head cluster, and then it will be orchestrated across all the worker nodes. And since Ravi mentioned in the beginning of the presentation, hey, Ray is able to scale. So when we enable the in-tree scaling true, based on the parameters that we have defined on the training script, in the case that Gabriel was showing us, the number of workers, number of CPU per workers, Ray can scale based on those metrics and scale the right amount of nodes for us. And to do that, we need to configure the workers. So for workers, basically, this is a pod spec definition like any other application that you deploy in Kubernetes. You have your limits, you have your resource requests. In this case, I'm saying that for each of my workers, I will need one GPU available, so one NVIDIA GPU. I could increase that, and Karpenter would take care of that for me to provision the right node. Since I'm defining a node selector and tailoring that to a specific Karpenter provisioner, we also can do a quick look in the Karpenter provisioner itself to see how it looks like. So we have one provisioning for training, one for serving, and one default. Let's see the training. So training here, I'm basically using G5s, 2x large and 4x large instance types. I found that to be the best combination for that particular model. So this is one of the responsibilities of the data engineer itself, understand the use case and pick the right instance. In this case, I'm using on-demand because I don't want to have any surprises during the demonstration for you folks today. So I'm using on-demand for that. And this is the way that we can tailor provisioner specific instance types using custom research definitions of Karpenter provisioner to provision the specific workers for us. Now, the most important parameter on your Ray cluster definition is the amount of replicas, right? So here is where we define the desired replicas, the minimum replicas, and the maximum replicas. In this case, we have 10 instances of workers. So just correcting Gabriel, we're using 10 instances. So we have 10 instances that are executing the training right now. And we could, for example, have that to 1 and minimum replicas to 1. And since we have enabled the in-tree scaling, we could apply that manifest. And once we submitted the job to the Ray cluster, Ray would increase the number of nodes up into the maximum replicas that we have defined in this manifest. So once you are not using those nodes anymore, you are gonna leave those nodes empty. So Karpenter is able to understand that and take those nodes down and scale back in again. So in that way, you don't waste capacity. So Ray is able to scaling, answering the question that was made previously.
Yes, exactly. I think the question that had come up earlier is that, hey, is Karpenter going to be able to destroy the nodes when we're not using them? Excellent. We want to make sure we're cost efficient. Yes, we want to take advantage of these powerful GPU-based instances, but we also know that those are not always the cheapest instances. Exactly. We want to make sure we use them only when we need to run an actual workload. Love to see that Karpenter, this cluster auto scaling, cluster management solution is coming together with these AI ML use cases. It really is, I think, the perfect marriage.
Yes, it's the perfect marriage, and it's the best way to do and the best way to scale nodes currently on Kubernetes. So if we go back to the jobs right now, probably the jobs should be ending by now. One thing that is cool about Ray is that we can drill down on all the specifications that is happening inside the training script. So right now we can see that we have the transformers.trainer, we have transformers.train, and right now it's executing transformers.trainer.save. So basically, our model was successfully trained and fine-tuned in the Ray cluster train, and now we have the model available on Amazon S3. And Gabriel is going to show us out how we can get that model from Amazon S3, generate a serving script with that model that we just trained, and then we're going to take the role of the data engineer and deploy that serving script using the operator mechanism of Kubernetes. So the stage is yours, Gabriel. Back to you.
Nice. So at the end of the training, as you can see, we have the checkpoints here in Amazon S3. And if we enter here, so we have here the time that it was saved. And the Ray, it's saving all the configurations, everything needed to retrain this model if you would need to do this, and also to serve this model, to deploy this model. This is what we're going to do right now. Okay, so back to the notebook. I'm going to get my model output. So here I can see the model path where we saved the latest checkpoint. And I have here a deploy script. So it's pretty much the same as the first script that I showed at the beginning. But the difference here, we are not anymore loading our model from the Hugging Face, right? Because this model, it's private. It's my model. I trained it with my data, and it's stored in my Amazon S3. So it's not an open source model. It's a fine-tuned model. What you can do here is to pass the bucket and the checkpoint prefix where my model is saved. And I'm loading my pre-trained model from local. So basically, I'm loading my model here from the Falcon 7B because the foundation model is still the same. But at this time here, I'm loading my fine-tuned model from my local directory. So basically, I'm getting the adapters, the new layers of that neural network that we created, and joining with the neural network from the foundation model. All right? Okay. So as the same, I'm going to store this in Amazon S3. And what I'm going to do right now, I'm going to create a zip file with this model and the serving script that Lucas can utilize it to deploy as a Kubernetes manifest.
So as of now, we just completed the first step of the demonstration. So now on my screen, we have the data scientist. So in order to automate something, we need first to understand how to do things manually, right? So we have all these steps on the notebook script. Would require us to automate that, getting those steps and put that in a pipeline, in an Airflow pipeline, in an Argo workflows pipeline, in order to automate that. Maybe you could be provision clusters only for training. Maybe you could have different business units with different requirements where each business unit can have its own cluster with its own set of serving applications, and then you can get that almost like a platform. But before doing that, we need to understand how to do it manually before automating something. So Gabriel just stored both training script and the serving script on Amazon S3. Now it's up to me to get that serving script and then deploy that on a different Ray cluster, because we don't want like things to mix it out, right? Because maybe when we're deploying that new application, some other folks, some other personas, some other people could be training other models in the cluster. So we don't want to use the GPU for training. We want to use another cluster for doing that. And since we're using the Ray operator, it enables us to create what we call a Ray service manifest. So let's take a look in what that Ray service manifest looks like. So basically, we are only able to create Ray service objects because we are using the operator. Again, benefits of using Kubernetes. You install an operator, you install custom resource definitions. Custom resource definitions will extend your API server, and because of that, you are able to create stuff, and I'm saying stuff because it could be anything actually, using this operator model. So in this case, we have Ray service as our custom resource definition. And here we need to define the name and the namespace where we're going to deploy that Ray service. And what are the components that compose the array service? So the first component is the application. So first we have the application definitions of what applications we want to serve in that particular cluster. So in this case, is the Falcon fine-tuned financial data. Two things that I want to highlight here. One is the import path. So basically, the import path needs to be the name of your script dot the name of the function to binding that script. So if we look back to the serving script that Gabriel created, we are going to notice that the name of the script is serve script, and the name of the variable that we will start that script, the entry point, is deployment fine-tuned. Another thing that is important to mention is the route prefix. So for example, in this case, we are exposing our fine-tuned model under /Falcon fine-tuned financial. So we could have more applications here. We could have one application for do one set of machine learning tasks. We can have text generation, we can have text summarization, and expose all that, all powered by Ray and Karpenter as provisioners to have the instance type. So almost like a platform, a self-service, self-managed platform for machine learning models running on EKS. Next thing that we need to define is the working directory. So basically, this working directory is where our serving script is hosted. So I'm gonna get that that URL that Gabriel generated before in the last step and place that URL here. So this is the new URL for our new fine-tuned model. One thing that is important to mention is we can install the libraries during runtime. So as example, we are using all those libraries in our serving script. So we can install that during runtime, and then we can define the deployments for that particular script. I could enter much more details, but you can have multiple classes, different classes in a single serving script with different models deployed in that serving script. So for example, you could serve different AI/ML models using the same endpoint but different classes. So Ray also enables us to do that. So here in this first application is our fine-tuned model. But also I'm deploying our non-fine-tuned model in the same Ray cluster just for us to compare the responses at the end of the demonstration. So as you can see here I have another list of definitions for another application. In this case, I'm defining the import path. I'm defining the route prefix as Falcon non-fine-tuned. So this endpoint will be the endpoint that will expose the non-fine-tuned Falcon model. So we are going to expose both endpoints under the same Ray cluster. So this is the first component of the Ray service application. The second component, Joe, is the Ray cluster itself. So the Ray service is a combination of serving applications and a Ray cluster. So you combine those things together, and once you apply that manifest, the operator will create a different cluster for you and also deploy those serving applications on top of that cluster. So with that, it's very, very easy to automate. We show it how to interact with Ray and submit training jobs using Python, but the Ray operator also has the job task as a custom resource definition. So you could, for example, use the Ray job instead of submitting the training on Jupyter Notebook, or for example, if you're using Argo workflows, maybe it would be better to use the operator because Argo workflows can create YAML manifests pretty well. Or if you are a data scientist and you are creating your pipelines, maybe you could be using Apache Flow, who is used Python behind the scenes to create a DoEKS and automate that. So you can do both, and for that reason, we show it both options on how to use Ray job submission and also the Ray operator. So here we have the cluster configuration, same thing that we had before for the training cluster, but in this case, I'm just provisioning 2 replicas because each model will be tailored to an instance because I want the full GPU of that instance. So right now, this is all the definitions are the same of what we have before. Since this is almost like a cook show because it would take a long time to spin up, I already have a cluster up and running with all those definitions, but I will apply that manifest for you folks to see Karpenter scaling nodes for us. So let me just change the name here to Ray Service Fine-Tuned 2 so we don't overlap the same configuration. And right now, I can go back to my terminal and show to you folks one thing. So here, as you can see, I have only 2 nodes with that particular provisioner that we are using. So I'm generating this using a provisioner name of GPU serve. So we only have now it's showing more than 2 nodes. Probably this is a bug. This happens to live demonstrations. Now it's removing, but we have only 2 nodes available in the training cluster. Now let's apply the manifest and see how Karpenter scales those nodes for us. So here I have my manifest, right? I have my race serve fine-tuned manifest that I just created, and I'm gonna apply that manifest to create the configurations for me. Now that I applied my manifest, I should be able to see other nodes becoming available for me, because Karpenter will notice that and it will start to provision different nodes for us. So let's wait until it starts to provision. In the meantime, we can see all the resources that Ray created with the race service. So we can get race services. It was created 25 seconds ago. Then we can get the pods. So for those pods, we are able to see that all those pods are in pending state. And then this is where Karpenter is gonna kick out to start to provision the nodes. So probably if we do a kubectl get nodes now, we should be able to see some nodes in unknown state. There we go. So this node was provisioned 37 seconds ago to handle that new capacity that we're saying that we're requesting because of those pending pods, right? It's gonna provision all the other nodes for us. We should be able to see the nodes increasing here. If we're not able, probably I ran out of capacity in my AWS account of G5 instances, but it should increase the nodes. As you guys can see here, we already have one node that coming up online 71 seconds ago. There we go, the node is not ready. So Karpenter is doing his job behind the scenes, right? Another thing that is cool is I need to show to you folks the GPU operator. So basically, the GPU operator is responsible to identify if those GPU nodes are coming alive. And if those nodes are coming alive, the GPU operator will deploy a daemon set on that node in order to configure all the libraries and everything that we need to configure. At the end of the day, what we will have is, sorry, wrong comment. At the end of the day, what we will have, wrong comment again. Okay, yeah. At the end of the day, what we will have, it's something like that. So we have the rate head pod running to orchestrate the jobs, and we have 2 worker nodes already running for me. So this is for the pods. What I can do is also I can get and verify my deployed application. So if I execute, for example, Ray kubectl get services, I'm going to be able to see that I have a head. I have another head service that is only for my serving application, and I have another service here. That service is exposing only port 8000. So Ray exposes a bunch of ports. Each of those ports are used for one purpose. So for example, giving a brief explanation around that, 8265 is used for the UI, for the dashboard. Port 8000 is used for inference. So because of that, we are able to see that we have the Ray service fine-tuned service here. And if we go back to the cluster now, we should be able to see the 2 applications already deployed. So as you can see here, this is my serving cluster, right? This cluster was provisioned by the operator itself, as you can see in this diagram. So once I apply the manifest, Ray operator will understand that manifest and provision the cluster for you, and also deploy the serving application on top of that cluster. So you actually don't need to do anything. You just need to apply the manifest. And that is the magic behind Kubernetes. For that reason, it's awesome, like controllers and operators. And you can also think to create platforms with that, because since we can have one cluster, we could have, for example, one cluster for one business unit. Or if we're talking about SaaS companies, we could have one cluster for different tenant tiers, where premium tiers could leverage their own clusters, where free tiers could have a shared cluster, for example. So the possibilities here are very infinite in the things that we can do. So going back to Ray right now, we have the 2 applications under serve. And just to show to you folks that I'm not lying, both applications are being exposed in the endpoint that I have defined on my Ray service definition. So just to confirm that, Falcon fine-tuned financial, Falcon fine-tuned financial, and then Falcon non-fine-tuned, Falcon, non-fine-tuned. So now we have a platform that has two models available for end users to consume. And this is exactly what we're going to do in the demonstration right now. So hand over to Gabriel, where we develop a Grad.io chatbot where we can pick the model and ask the same question. Remember the question, guys.
Yeah.
Why do I need an emergency fund if I already have investments?
There we go. And Lucas, I think that was an excellent overview. And I want to go back, just building up a little bit more tension for Gabriel to show the final result of the model here. But I do want to go back and call out that you mentioned something very specific. You said, the reason why we go through this laborious process of the manual steps is because when we have this automated, it's going to be that much easier the second time around. What you've shown us here is the fundamentals to have an automated flow for fine-tuning models so that once we have all this set up, tomorrow when our data scientist, Gabriel, who's been acting as our data scientist today, when he wants to fine-tune the model further, he just changes the data set that's provided, hits that play button, and then all of these steps can be automated. We've built that foundation here. It's not only automated, but they're built on EKS best practices. They're cost optimized. We're using Karpenter to make sure we're using the right type of nodes only when we need them. So love the model here. Love all of the different kind of technologies we covered. But realistically, this is kind of a day one thing. Once we've kind of matured this platform, it really does become that much more straightforward to further fine-tune the model. But here's the moment we've all been waiting for, about over an hour of showing the actual technologies. Thank you guys so much for all of the kind of details here. But we want to see, what does that fine-tuned model tell us here when we ask that question? Gabriel, back to you.
Nice. So I have here a Grad.io application. And just to remember, the first model without fine-tuning, I have this question here. Why do I need an emergency fund if I already have investments? And the no fine-tuned model answered, you need an emergency fund because you don't know when you need it. So it was a not good question. So for now, what I'm going to do, I'm changing to the financial Falcon deployed model. So it's going to call the other endpoint. And I'm going to do the same question. So it's going to take some time because we are utilizing just one GPU for this model by design, but we could scale in your serving script, we could ask for more GPUs. Okay, so let's wait.
Tension.
Okay, now we have the answer here. And now you can see it's a good explanation what is and why you need an emergency fund. So for example, the amount of money you should have in your emergency fund depends on your personal situation. If you are single and you have independence, you may only need a few $1,000s in your emergency fund. However, if you are married with children, you may need to have a larger emergency fund. There are a few ways to start an emergency fund and a lot of explanation how to do it.
So Gabriel, I gotta say, this is really cool because what you gave it more information, more Q&A type questions about financial data, but feasibly, let's say a financial institution that actually has access to your financial data wants to create an experience personalized, catered to you based on your finances. They could do exactly that with this type of fine-tuning. They could do it in a private and secure way where your data stays within the company's servers without being, exposed to third-party services. And, feasibly, after looking at this response, you might say, hey, you know what? Maybe we shouldn't lead with whether you're single or married. Maybe we should already know whether this person is single or married. And we could fine-tune that model even more for this particular person. I think that's pretty cool. And honestly, congratulations, because the demo worked. It was really cool to see how you can fine tune a model in just over an hour. That's pretty impressive.
Yes, it's pretty good. And as you saw, we trained it just with with a small data set, just with 1K examples. Imagine what we can do with more data.
And imagine the potentials of that scaling, right? So since we're using Ray Operator, we could even plug our GitOps pipeline. Many customers are using GitOps. Everyone is going to a GitOps path in Kubernetes. So GitOps is able to apply manifests. And since Ray service is a manifest, you could leverage the same structure for GitOps and Ray being just another application that you have in your stack.
So, folks, I know we're a little bit over our usual time today here, but I want to make sure for our folks following at home, is this outside of the bounds of reasonable for the average individual to go through, or is it completely reasonable? Like, how can an individual that's interested in this tech get started?
So I think, Ravi, do you want to comment around that? Talk a little bit about Dayton EKS and the project that we have?
Sure, yeah, absolutely. So if you're looking to get started, all of the stuff that we talked to today, the sample code, is available on the repository that was shared earlier. Maybe Sai, you can post that again. At the same time, we built blueprint for some of the most common use cases that we see while helping the customers, right? So for instance, on the AI ML side, we have JupyterHub for model experimentation that we looked at here, deploying Ray clusters, for example, on EKS, and many more others, right? At the same time, check out this repository that Sai just pasted. It covers all you need to get started, but also scale efficiently, right? So as we saw in the demo, it sets up your environment with Terraform to using Karpenter for custom resource allocation, to deploying JupyterHub for development, and Ray operator at the end for optimizing the serving, right? It demonstrates how you can set up a cost-efficient multi-tenant ML platform on EKS, right? So use this end-to-end example to see how you may want to build out a use case that's relevant for you. So in this case, it's the chatbot, but the same concept applies if you're thinking about text summarization, for example, right? So that might inspire you to consider some of those use cases as well.
Absolutely. And Ravi, all of this is kind of automated and, at least templatized in data on EKS, right? Tell us a little bit about the data on EKS project. I know we've covered it in the past before, but specifically this use case leverages that project heavily, right?
It does, absolutely. So all the building blocks that we use as part of the project, so for instance, setting up JupyterHub, setting up running the Ray operator on EKS, all of these are captured as blueprints on the data and EKS project, right? Data and EKS project is all the learnings that we have seen based on what we see customers running in terms of data and ML workloads on top of Kubernetes environments, right? So that's what we've tried to capture in terms of reference examples, blueprint implementations. It has infrastructure as code samples, in some cases some benchmark reports as well, and that is a central repository in this case for you to go check out in terms of how you can use some of the stuff that we put out there in terms of customers wanting to run different data and ML workloads, right? Or using these blueprints to build different data management and ML platforms on top of a Kubernetes environment.
Excellent. And one last opportunity for folks in the comments, if you want to ask any questions, or Gabriel, Lucas, Ravi, any final thoughts, any closing statement that you have for folks that find this interesting, maybe want to get involved, want to learn more, anything you
I just want to say thank you for hosting us and having us in this session, which was actually amazing. I think I have a lot of experience with Kubernetes, and I've started to work with Gen AI this year. So like ever since the beginning of the year, February, me and Ravi, we have started to build stuff, learning stuff. And I would say that the best way to learn and actually see how the things work, it's get your hands dirty. So you are able to understand all the concepts of that if you get your hands dirty. For me, when I started to learn that, didn't make a lot of sense. But once you start to get your hands dirty, you start to see some patterns that are very similar to patterns that you have seen before, like deploying applications, building CI/CD pipelines. And at the end of the day, when you understand all those moving pieces and how those moving pieces connected together, make it much faster for you to accelerate your deployment of that solution. And even and since we're using Terraform for templating powered by Dayton EKS, you can have that environment in your account in more or less like 30 minutes, because it would take a little bit for the EKS to be up and running, RDS to be up and running for the Airflow. But it's all templatized, it's all available, open source. And I think this is all that I had to do with my close comments here for today's session.
Awesome. Excellent. And for our folks that are viewing at home, I know a lot of times there's students that are looking to get into data science, or even folks in the industry looking to make a pivot to focus more on data science. Can I ask the folks at home, can they reach out to you, Gabriel, Lucas, Ravi, and what's the best way to reach you? Maybe LinkedIn or Twitter?
Yeah, I think so. I think on LinkedIn you can reach us out, and you just search like Lucas Duarte. That probably you're gonna appear to you in the same way that it's written here.
Yeah, absolutely the same. Reach out to us over LinkedIn, Twitter, anything works.
Yeah,
Awesome.
the same.
Excellent. All right, folks, you heard it. Please reach out to them if you have any other questions. If you're watching, you want to see more videos like this in the future, be sure to subscribe to Containers from the Couch. Thank you for joining us for this awesome episode focusing on fine-tuning generative AI models. We'll catch you all next time.
Thank you, folks.
Thanks, folks.
Thank you.